So, welcome everybody. Today I will be dual. I will be from home because you can hear the voice and doesn't look good. But in the classroom there's Barbara, which will be streaming me. Let me see if I am visible. I'm waiting for the thing to see if I will appear in the classroom or not. Right. I mean, I should be also audible, at least in the class. Yes, very good. So, as I promised at the beginning of the course, everything will start at the end. Everything will be compressed in a few rules and in a unique view. And the aim of this last lesson is exactly that. So the plan of the day is that we first do a closure of the course, wrapping more or less all what we have seen in terms of concepts. And then I'll present some of the projects that we propose you to do, and also together with the rule of the exams. And in a second part of the lesson, Barbara will show you two examples of exercises that are representative of the exercises that can be found at the exam. Okay, so let's start with the wrap up, and as every good wrap up, we start from the beginning. If you pick up one of the first slides of the course, you will see that my contract with you opened with the promise that I would have taught you a set of tools, and we would have applied these tools to different domains, which are representative of the problems that can be solved with the tools themselves. Particularly, we have seen quite some filtering. So the first part of the course was on the filters, discrete filters, Gaussian filters, and particle filters. And this was more or less the first part, which included somehow one part of data association, in particular the greedy version of the data association we have seen, the one that required prior. In the second part of the course, we focused on an offline estimate or a batch estimate of the state of the dynamic system, and then we have introduced basically Gauss-Newton and its variance, and we have unveiled the structure of the problem and devised a methodology that allow us to approach even large problems with large batch estimation problems. And in this context also we introduce new techniques for data association that relax the assumption of having an initial guess, for instance, Runsack, that falls into the voting schemas. I did not talk about spectral methods. My pity means that I will not ask about spectral methods. In terms of calibration, well, of applications, we have seen plenty of applications, mostly in the exercises. Now, this makes me focusing on one aspect. We use the exercises to present you realistic problems and realistic applications. In fact, some of the exercises should have been a lesson of theory that I would have had to explain you, but in fact it wasn't, and because I prefer to present these topics as if they were as if you had to resolve them. So in this way, you basically have much more grip on the solution which is presented, and I think it's more interesting. However, this also means that the exam, that is typically structured in two parts, one theory and one, let's say, practice. I'm talking about the written exam, the written test. The first question will be might comprise also exercises that the tutor Barbara has developed on the Blackboard, right? So bear in mind that every single piece of the course that we made in the class might be asked to you in the theory part. Exercises can be anything and typically involve any one filtering, one least squares, and one Runsack. All right. So now this was just an overview of the thing. Now let me present you the wrap-up of the first part of the course, where in this slide basically we have facts, tools, and problems. Like the pink things, these objects over here, are problems that we have solved that served me to introduce the methodologies behind. The orange ones are, let's say, assumptions or facts, yeah, typically assumptions, or as I said, facts. And the blue ones are entities, so to say, or tools. Now, everything starts from the reality, and our goal is to estimate, in the case of filtering, was to estimate the state of a dynamic system during its evolution, right? And where do we start? We start from the observing the reality and then starting to construct a model of the system. What is the state? What are the measurements, and so on. Normally, in making this model, we're lazy, so we might decide not to go into the finest possible description of that particular system, just because maybe we can't measure everything. One example is, for instance, in the odometry, if we have access to the wheel encoders, so we might decide to integrate the odometry, so to evolve to the next state just by using the first order approximation instead of a more complete model that considers more powers of the Taylor expansion. So we might do that, and so we lead to a poorer modeling, right? So in the end, what we have is that the model that we have is not that as accurate as we would like it to be, because we decide to make it simple. And on the other hand, we might have also that noise that arises from sensors, from unmodeled effects, makes the system not deterministic. This means that what we are able to observe is only one possible hypothesis among the many that we could observe having the very same state. So we can describe the probability of an observation. So we can describe an observation made by the system, which means an output of the system, as a probability distribution. Similarly, we can describe the transition of a state transition of the system as another conditional probability distribution. Anyway, we made some effort in modeling the system, and we could embed these efforts into the probability language by exploiting the structure of the phenomena that we highlighted during the modeling. And therefore, we convert our funky deterministic model into a stochastic model where instead of having direct functions that map a state to the next and that map a state to a measurement, we have conditional probability distributions. Once we have a system that is characterized by conditional probability distributions, in particular the observation model and the measurement model, we could use the generic implant of Bayesian filtering that we have, and we have seen that all possible filters in our that we have presented in the course, they basically all follow the very same derivation. They come from the very same machinery, which was the Bayesian filter derivation that used the chain rule and conditioning for the state chain rule and marginalization for the state transition, and chain rule and conditioning for the update. So we have defined this demonstration, so to say, of the filter, and then we started deriving different algorithms which were implementing this very same constructive proof, and the different filters, they basically differ from each other from the assumptions that they make on the underlying probability distribution. If the state space is discrete and finite, then we could use a histogram filter and directly apply all the rules on probabilities that we have seen on the grid. If the belief is assumed to have a Gaussian distribution, and so the measurements, and if the system is linear, then we could exploit the fact that the Gaussian distribution is closed under a lot of operations, and we could use a Kalman filter. But also under mild violation of the linearity of the system, the Kalman filter, that then turns to become an extended Kalman filter in this sense, might be used by locally linearizing the transition model and the observation model to reduce the system to an affine form that can be dealt by the original Kalman filter. Pain of the Kalman filter was to construct the Gaussian, to construct the derivative of the different functions to calculate the affine form, the locally affine form characterizing our system. And so we started to investigate a new way of representing Gaussians that would allow us to calculate the probability distribution of a random variable that goes through a function in a way that does not require to calculate Jacobians. So basically, if you recall the uncentered transform, the big game was to represent the Gaussian as a set of samples, and then to pass, in order to calculate the effect of a function to a variable that follows this distribution, what we were doing is to use this set of sigma points, especially deterministic samples, pass them through a function, and then once again reconstruct the Gaussian from that. This was the game of the uncentered Kalman filter that leveraged on the uncentered transformation. And then, of course, we on all these problems, on all these tools, we provided an immediate implementation. For instance, in the case of the discrete filter, we used the grid. We have shown you grid localization. For EKF, we implemented basically everything, 2D SLAM, 2D localization, and so for the UKF. And also, but there was one aspect that we didn't address directly in this formulation of exact filters, in particular, let's say analytic filters, which was the fact that we needed to perfectly know which measurement was corresponding to which part of the state, right? And this problem is the so-called problem of data association that arises from the fact that often by looking at the measurement itself, you can say what is what. You see just like points and you don't know which point is which. And this made us decoupling the problem of constructing an estimate which is affected by sensor aliasing into a problem of determining what sensor, what measurement belongs to which state variable, which means measurement landmark in this case, like to picture it, and once this is known, we conducted the next estimate by running filtering. To this extent, we introduced the problem of data association first in its general form, and then we boiled it down to 3 simple heuristics, which are the most commonly used in the case of the filters. Remarkably, one should consider that the data association would lead to issues in data association, if we want to still carry on the estimate, would lead to a exponential growth in complexity, because at every new iteration we would have to add a certain number of hypotheses which is let's say equal to the previous hypothesis multiplied by let's say a certain factor. So like if you do this over and over, every time you might have an exponential branching. Instead, with the mechanics of data association that we have provided you, one performs a suboptimal choice, but just like picks up at every point in time the possible best association, and then it forgets basically the remaining part of the association tree. This is a choice that you're forced to do in case you're using a Gaussian filter, because a Gaussian distribution doesn't allow you to represent multiple modes. However, if we relax the assumption that our distribution is Gaussian and we are willing to pay a little bit more computation and memory to represent a distribution in sample form, we could partially recover this from the greediness of performing single hypothesis data association by using, for instance, a particle filter, which is a filter like any other, but in this case, since the probability distribution is represented by an arbitrarily large set of samples, you could calculate the likelihood. You could evolve every individual point or sample of the distribution of your probability distribution according to an independent hypothesis for the data association, and we have seen it in the case of localization. But this was more or less the game and the story of the first part of the course, the one that most of you have done. And then let's say if you're given an exercise on filtering, what do you need to do? Well, which is basically which methodology are you supposed to apply? And then Barbara will illustrate the stuff more in detail. Well, if you're given a filtering problem, the very first aspect that you have to do is to qualify the spaces, which means you're given a dynamic system typically, and you have to tell what is the state, what are the controls, and what are the measurements. And remember that in doing this qualification, you have to characterize the entire domain of the quantity under analysis, and also the way you're going to represent it mathematically. If we're talking about a Gaussian filter, remember that the parameterization should be at least locally Euclidean. Once you've done that, and you have your system at end, or the domains at end, you have to qualify the transition function, which means basically write down the f of xt minus 1 comma ut minus 1 that calculates xt, or just shift both by 1. And then in order to calculate this function, you have to ask yourself, okay, given that this is, I think it's the state, how can I calculate the subsequent state? And then from also considering the controls potentially. And then by basically looking at the system, you will be able to answer to that. And the second aspect is, okay, typically you're given a sensor in this exercise, and in order to answer how to write down the measurement function, you have to look at the model and try to elaborate an algorithm that, given a complete knowledge of the state, will tell you what are the measurements. And then in doing this, there's a very relevant aspect that we might want to deal with, which is, do I have enough information in the state in order to predict the transition or in order to compute the measurement? Because sometimes, even if we're interested in tracking a state which is only a portion, we are only interested in a part of the state which is a portion of the completely available state. I mean, to make you an example, imagine that we are observing an object that moves in the space, and we are tracking this object that moves in the space, and we have no whatsoever way of directly measuring, let's say, the odometry of this device, because we are observing it externally, right? Like if we wanted to implement a filter that tracks the position of this object in the space, well, the thing would be, assuming that this object was here, where will it be next, right? Like we will have to qualify this position of the object will be for sure in the state, but would just the position of the object in the space be sufficient to predict its next position? That's the question. And the thing is that if not, we might need to augment the state with, for instance, the estimated velocity of this object. Then, having the velocity of this object, we might predict, assuming that it has a linear constant motion, we could predict the next position. So we are allowed to add to the state whatever we need to predict the transition, but not only. We are also allowed to add to the state anything we need to compute the measurement. Okay? And then the second aspect that we might want to ask ourselves is, are the parameters of my system conformant with the operations that the filter does, which basically means it calculates the difference between the prediction and the measurement, and it calculates and it applies the linear perturbation to the, vector perturbation to a vector parameterization to the state. And this moves me, now that we have done it, also to the manifold aspects. And you might ask yourself, hey, do they exist? Are there existing filters that support the manifold formulation, so that allow me to represent a state that easily states that are on manifold objects? And the answer is yes. These are that's a splendid paper that leverages on the box plus operator. For those of you who are interested, I think that we will put a link. But in this course, it was premature to introduce the manifolds at the filter, because then I would have taken even more time than what I've taken. But with what you have learned about the manifolds in the least square part, you could straightforwardly understand how filters at the manifolds can be implemented. And this more or less closes the first part. Then there was a second part that still captures the same phenomena, but uses different tools. The game is always the same. We have reality, and then due to poor noise modeling, by using the probabilities and by using the structure of the system that arises from having identified the model, we could, and assuming that the system is locally, the distributions are locally Gaussian, we could construct the least square machinery. Right? So we started deriving this least square machinery at the very beginning, formulating it basically as if it was the update step of a Kalman filter, if you want to see it this way. By doing this game, we have figured out assuming, remember, the least squares assumes that under the hood I have a Gaussian distribution, or at least a monomodal distribution, we addressed leveraging on the proof of the Gaussian conditioning. We have figured out that a least square problem also allows to calculate the uncertainty of the estimate, and we have found out that the H matrix represents the information matrix of the estimate, and as such it might be rank deficient in case there are variables which are not observable, or in case I have an underdetermined subspace into the in my estimate. And this was, for instance, the case of all the multi-pose SLAM problems, where basically one solution was valid as all other solutions obtained by the first, by moving, by translating and rotating this one solution in the space, leading to a 6 DOF of uncertainty. And we approached basically with least squares all sorts of registration problems. Particularly, we started with 2D, 3D point registration, calibration, and so on. In contrast with the filter, with least squares we introduced, we explicitly addressed the non-Euclidean spaces by introducing the manifold mechanism. Basically, the game is that whenever either the state space or the observations of my system are live in a manifold, what I can do is to trick the iterations of least squares by calculating a locally linear approximation of the system at a point calculated with respect to a chart of the manifold calculated at the current optimum. And the origin of this chart is going to be 0 at the current evaluation point. In this way, we put ourselves away from singularities. By doing this lifting, we were able to seamlessly approach 3D registration problem that otherwise would have required some more complicated handling of the wraparounds, which also renders the whole formulation less elegant. And also, we had fun because we could approach all sorts of registration problems. Linearity, which is rotation, translation, and scale, or projective when we have a camera. Clearly, similar to what we have done in the filtering part, we needed to tackle the problem of sensor aliasing, which means basically wrong data associations. If we have few wrong data associations, which are clearly, and if we have an initial guess, then we could deal with the few wrong data associations by using the robust kernels that basically neglect those measurements that have a high error, assuming that most of the good measurements will have a small error. And this is done by within every individual iteration of our least square machinery. If we are in a situation which is a little bit worse, we could use some sample-based consensus that is Runsack, that we have seen 2 lessons ago, of which I will talk in the next slide. Another aspect that we have observed in least squares is that sometimes so I need to iterate whenever my function is nonlinear. My error functions are non-linears in general, and also clearly when my domain is non-Euclidean, because in this case I will have to do some wrapping in the game. But then we introduce another technique which is called linear relaxation, that says, you know what, if you have enough constraints, you could forget about some constraint that you have in the domain, and you could boil down an error function which assumes that the state is completely that you don't have any constraint on the variables representing the state. And this technique was linear relaxation. In particular, we used it in ICP and to calculate the relative position of between 2 point clouds. And we used the linear relaxation by dropping the constraints that the three axes of a rotation matrices should be orthonormal and unit norm, just like forgetting about this, calculating a matrix that would be a rotation matrix if everything was fine, and then turning it to a proper rotation matrix by SVD decomposition. But the general schema, the general game of linear relaxation is I have some constraints on my state. What I ignore these constraints, I calculate a solution by ignoring these constraints, and then I modify this solution in a way that I get the closest possible approximation that respects the constraints by using some other techniques. And that was linear relaxation. Once again, by looking at the structure of the system, what the system, with system I mean the phenomena being tracked, we might also leverage the fact that for large problems with large state spaces, most of the measurements, they only involve very few state variables, and this typically leads to a sparse structure. We also have devised a unique, an important formalism. I mean, even if we did it in the last lesson, I would say that this is the most important thing of the entire course, which is factor graphs. That it's a way of writing down and of describing complicated, large-scale estimation problems involving least squares, but also just to represent them, and then to feed them to some specific solver that probably you will never write, but you can use, and some of them are available, also made by me and us, the group. By using these mechanics, we are able, of factor graphs, we are able to represent in a unique way and in an additive fashion different phenomena in SLAM, like pose graphs, which is what we have seen last time, multi-point registration, and multi-point registration, which is when the robot measures a sensor, but we could also add inside, let's say, vision sensor that measures only the direction of a point, but not its distance. We could add some kinematic parameters that need to be estimated that would enter in the system. We could add the position of the sensor that is unknown that could enter in the system. And all these sort of things would be easily handled by formalizing the problem with factor graphs. And then, in order to use it, to understand this tool, what we introduce is the methodology that now should enter really like in your skin, which resembles pretty much the methodologies, the methodology of the filters. Once again, once you want to approach a problem, first you look at the problem and you baptize the aspects. Once you look at the system, you say, what is the state space, remembering all the hints that you use for filtering. You qualify the domain. You define, if the domain is non-Euclidean, you define an Euclidean parameterization for the perturbation. Once you have the two, you could define a box plus operator that allows you to calculate the next state from the previous state and the perturbation. Consider one thing, that when I talk about next state in least squares, I mean the next state estimate, the next iteration. When I talk about the next state in the context of filtering, I mean the next state in time. We do the same. What we have done for the state space, we do it for the measurement space, qualifying the domain. In contrast to the state space that needs to be added, needs to be modified, the measurement space doesn't need to be modified, but we need to calculate the difference on the measurement space. And therefore, we need to define a Euclidean parameterization potentially for the perturbation along the measurement space. And we need to define a box minus operator that, given to manifold elements, tells us the vector difference between the two, which is construct a chart about one of the two and calculate on this chart the position of the other one. Once we have done this horrid effort on the state spaces, we can identify the prediction functions that are like the measurement that I should get. Remember that while identifying the prediction functions, you always consider that the state is known. And your task is, assuming that the state is fully known, what would I see there? Once you have this, you can define the error functions as a difference of box minus difference between the prediction and observations, and you're done. Then the third thing that we introduced very shortly is another tool that we introduced was the methodology of Runsack. You might have exercises that involve Runsack, and also in this case, if you want to use Runsack, the Runsack schema, we have a set of routines that we need to obey. We need to have, very first thing, we need to have a procedure that seeks for the correspondences, right? Whatever, some heuristics on the data, comparing the descriptors, something that allow us to determine the correspondences in a more less random way. This is my neighbor that adores when I'm giving lesson, right? Can you hear? No. No, you can't hear it. But I do. Once we manage to identify reasonable or not ugly, not impossible data association between two set of data, we might want to devise a procedure to select intelligently a set of correspondences from this large set. How many? The minimal set, because we need to, the game of Runsack is to use a minimal set of correspondences to calculate the solution and then to validate the found solution by calculating the error of all the remaining correspondences, right? So we need to have a way of matching features, so to say, a way of determining a possible set of n correspondences between features that allow us to find a stable solution. For instance, in the case of ICP, would be very stupid to determine the correspondence between three collinear points into point clouds, right? Because if I have three collinear points, 3 points that lie on a line, even if I align them, I will have 1 degree of freedom because there will be an uncertainty one in the solution that doesn't really help me in determining the correspondences, by evaluating that solution. Would make a lot of sense to take a triplet of points in the one cloud and in the other cloud that have a similar structure and that can be overlaid with each other, and possibly that they are quite far from each other, because in this way, let's say I'm gonna find a stable solution. Like this is a procedure to smartly select a pseudo-random set. I mean, how many points? Well, clearly I need to calculate to have an algorithm that, given a minimal number, but really minimal number of correspondences, allows me to calculate a solution. And here you can use your fantasy, really. I've taught you two. One was the 8-point algorithm for determining the essential matrix or the fundamental matrix between two images. Another one was the linear relaxation for ICP. These are direct approaches. Clearly, in order to calculate the solution within Runsack, you need a direct approach for finding it, because you do not have a data association. And another thing I need for Runsack, am I done? I have a procedure to determine somehow the correspondences between the set. Let's say a feature comparison. I have a procedure to select, given a bunch of potential correspondences, to select a minimal set of correspondences that if solved would lead me to a stable solution. Okay, fine, I have it. Clearly, I need to have a way to calculate such a solution. And then the final thing that I need to have is a procedure to count inliers, which is basically a way to tell which correspondence of the initial set is good after I have applied the transformation that I have found in the first, in this iteration. And then basically this concludes, like if I have these ingredients, I could implement Runsack. And once you will be going to work to do the thesis, not necessarily with me, but if you want to do it with me, okay, it's fine, I'm happy. What I want to say is what are the you will have to do a lot of debugging. This is like really the essence of this job, because sometimes the problems and the programs are relatively simple, at least in their core version. The problem is that once you mount it in reality and once you feed it with real data, you will figure out that a lot of assumptions that you have made at the beginning have to be relaxed. And so normally you enter in one of these loops where you have to amend the system and change it slightly, or add some component or remove some other component, and like it's basically an evolutionary approach until when it works. Okay. Clearly you have to be honest. Like once I debug and I design one of these systems, I always start from a simulation. I always start from an ideal world, a synthetic environment where everything has to be as I think about it. And then the very first stage is to debug the simulator. So that means to see if the data coming from reality have some connection with the data that arises from the simulator. But since simulator means a synthetic problem generator. Once you have this, then you start adding, approaching the different aspects every time by looking at the ground truth and stopping every time you don't get the solution you want to have. Okay? Because that's probably a mistake, an error. And also, sometimes it might happen that the street that you have taken to solve that problem doesn't really work. But this is fine, because you at least made the simulator that allows you to quickly test another approach that on that very same problem might work. My recommendation, so for when you do the project, is like visualize the data. When I give you the raw data, you should be able to visualize them. Visualize every single step. Don't print them on the terminal. Like really visualize it. Visualize them. Do plot. Do images. Do something, because it's very hard to spot the data from a plot, from a writing on the terminal. Second recommendation when you do the project is that the error in zero should be zero, and this you verify with the simulator, or clearly in the data we will provide you with some noise-free data as well. Remember, when you are programming, that the more trivial is the task, the more likely it is that you make mistakes in that task, because you basically do it overlooking at it, and then this is the moment where the evil of the programs kicks in. And the final one is like implement and fix the things dynamically. So you write something on a paper, then immediately test it, because sometimes it's much you can directly validate the theory with the practice. And this concludes the first this wrap up on the course. I hope you enjoyed, and I mean I would have done more if if we were all in presence, but yeah. And then the second part of this episode will be presenting projects. All right. Now, these are some of the projects. If you have really are carving for a different project, you can, you know what is the subject of the course, so you can propose a different one. But these are the default projects that we provide. I mean, the rules are here and are quite simple. First one, the projects are individual. I repeat it, one project, one person. Second rule, the projects has to be linked to a shared Git, to a private Git repository shared with us. The staff is Barbara, me, and Tiziano. Before doing the exam, you need to be sure at least of having chosen a project, okay? You don't need to have completed the project, but you need to have chosen it. Why that? Because it's at the moment when you choose a project that we register you and you become part of our bookkeeping exam. So, I repeat, if you want to do the exam, you need to, the written exam, you need to first do the project. Is that clear? Then, for each project, we're giving you two things. We're giving you the ground truth of the solution, noise-free data, and noisy data. Okay? Now you hear it, right? Noise-free data and noisy data, right? Now, in what the project is typically a program, the evaluation of the project consists in running your system on different data from the one that we have given you for calculating the solution, but clearly similar. No, it's not that they will have an insane amount of error. The project makes you, without project you don't pass the exam, let's say this way, or you pass the exam but with a penalty of -4 points. It's a special case, but normally the project allows you to a small grade adjustment, +/- 1 point. Okay? There is a special case of some student that says, Professor, I'm getting the master, I need to get the master next week, I really need you to verbalize the exam, but I haven't done a project. For these, and for these special cases, if like I needed to handle these special cases, for instance, sometimes there are people in Erasmus that need to finish the exam before time, and then they need to have it verbalized. And so, like, we devised that in this case, if not handing in a project makes an exam -4 points with respect to what it was, to the grade of the written exam. Do the project, that's the suggestion. Now, here is the list of potential projects. First one is beacon calibration. Like, beacon calibration is, I have a set of 3D points in the space. I don't know where they are. And what I sense is from each point, each beacon, I sense the range to a set of nearby beacons. Right? So a set of distance between 3D points. I do not have an initial guess. What I want to have is, after having measurement of each beacon with each other, or each subset of beacon with each subset of other, I'd like to have a hypothesis of their position in the space. Clearly, I will not be able to resolve a rotation and translation in this case. And there will also be a potential specular reflection. But I'd like to have, to calculate the position of the beacons that minimizes the relative transformation, that better predicts, so to say, the range measurements between them. Second project is quite simple. The input is that we have a 2D robot that is moving in the plane, and the robot observes landmarks in bearing only. It has an odometry. The observations are labeled. What I want to have is the trajectory and the map using least squares. Okay, bearing only slant problem using least squares. Remember that you will have to triangulate a landmark. The third one is also similar to the previous one, only that instead of having bearing between landmarks, I have ranges between the robot and the landmarks, right? So I can only measure the distance. Again, on least squares, no Kalman here. Then there is a third one that is a little bit more complicated, but it's really nice, which is visual odometry. Your input are camera parameters, which means the camera matrix, an image sequence where each image is described by a sequence that consists of a ID of a point observed, and UV are the image coordinates of this point. Clearly, we assume to know the position of the points in the image. And like given this, I'd like you to construct a visual odometry. How to proceed? Well, I've told you, given a pair of images, how to determine the rotation and translation by using 8 points. You can register the first pair using epipolar geometry. You impose a scale because you will not be able to calculate the translation. Once you have done that, every new image will be added to the set with its own landmarks. Then you could use POSIT to calculate the relative position between the new image and the previous constellation of landmarks. You could triangulate the new landmarks and go on for a while. Every time, clearly, you will have to add the new landmarks to the map by triangulating the open ones. So there's a little bit of bookkeeping to be done. At the end of the game, you will have a set of camera positions, you will have a set of landmark position, and you want to do BA at the end, which is basically implemented in total least squares. There is the fifth one, which is a simplified version of that, but of 4, which is planar monocular slam, which is basically the slam system that runs on an automatic hoover like the Roomba. The game is that we have robot with the odometry, so to say. We have the camera parameters, which tells us where the camera is located on the robot. And we have points. Basically, it's the same as the previous one, with the difference that the robot moves on a plane instead of moving in the space. But what we also want to do is to estimate the to keep on tracking the landmarks. All the projects have to be done in least squares. I mean, what we want to do is also to be able to close loops. Okay. All the projects have to be done in using least squares. So the difference between this project over here and this project over here is that this one here is 3D, but if after a while you don't see any more a landmark, you can remove it from the state. In this project here, every time you see a landmark and you triangulate the landmark, then you have to be able to redetect it in the future. Right? So this is a full slam thing. How do you get a project? Well, you write to these two people, now basically only to Barbara, and you use this subject, prob rob, you write your student ID, and you wait for instructions. And you will be given with a folder which contains the material to pass the exam, to hand in the project. All right, now I think I'm pretty rotten, and I would leave my voice to Barbara, that will present you two exam exercises. Barbara, are you ready for the synchronization? Tell me when I should stop the streaming via Telegram. Barbara? Shall I stop? I will stop now.
Okay. Probably I just started the streaming, but I'm not sure. Mi sa che non ci siamo agganciati. Ok. Okay, then let me put away the mask. Okay. It seems we are on air, so I can start with the exercises of today. Today we will see two least squares exercises from a sample of an exam of probabilistic robotics. In your folder, in the folder exercises in probabilistic robotics 21-22, you will find two examples of exams. So, as I was mentioning, I will mostly focus on the exercises where we can talk about Runsack and least squares, but in this folder you find this PR exam sample A and sample B, where you also have an example of a theoretical question and an example of a filtering exercise. So in this sample A, you have that the question is, for example, least squares, derive the Gauss-Newton algorithm, motivate the fact that the coefficient matrix H at the equilibrium is the inverse covariance of the state. And of course, if you can remember the slides about least squares and about least squares and uncertainty, you should be able to answer this. And then the second exercise is a filtering one. It's very interesting because you will have the opportunity to see P-null camera model applied to a filtering exercise. But we do not have the time now to go through all this. So I would suggest that we go directly to Runsack, that you have never seen an exercise. And then we'll eventually come back to this if we have time. But please at home have a look, and if you have any doubts, just write an email. So, okay, here we are with the exercise fit the circle, talking about Runsack. May I ask you to move there, otherwise I cannot see you. No, with the because you are only 3, and if I cannot, I have the monitor that doesn't allow me to. Okay. Okay, so it's easier for me. Okay, thank you. Okay. This exercise is entitled Fit the Circle, and the scenario is given a set of points on a plane. We want to find a subset of these points that belong to a single circle of a known radius and center. So you have a set of points and you are asked to find the parameters of this circle that fits with a subset of these points. The problem tells us to use Runsack, and of course, if we have to use Runsack, then we need to define the parameters to be fitted, a minimal solver to use, and an error function to determine inliers and outliers. Let us go a little bit into more details. So as you remember, in Runsack, what you do is you randomly sample a set of samples from this set of points, and then you try to find, by using a minimal solver, a value for the parameters that fit with this subset of samples. Then once you find the value of the parameters that fit for this subset of the samples, then you determine how many inliers and outliers you obtain with this model. In order to do this, you need to define an error function which allows you to determine whether a point is an inlier or an outlier. So this is how we can explain each of these questions in our question 1. Then question 2 asks, given a set of inliers and an initial estimate, formulate the least squares problem to optimally refine the parameters by considering only the inliers. Indeed, as you might remember, in principle, we could directly use least squares to estimate the parameters of our curve, which in this case is a circle. But least squares is affected by outliers, and indeed you remember the robust estimators as a possible solution to this. But even more effectively, you can use Runsack and then use least squares only as a tool to refine the initial estimate provided by Runsack. Of course, in order to do this, you need, as usual, to formulate the least squares problem, which means define the state, the error, and the dimension of the Jacobian. Then the third question is very simple. You will see the solution. The third question is, assuming that the inlier ratio is 10%, meaning that only 10% of the points belong to the circle, the question is, how many rounds of Runsack are needed to compute a solution with probability p equal 0.99%. If you remember, the meaning of this is that we are asking how many rounds we need in order to be sure to get a set which is only composed of inliers. Indeed, we are able to compute a solution when we take a minimal set of samples that contains only inliers, and this will be our solution. So, if there is anything that you do not remember about Runsack, so that what I said so far is not so clear, then you can ask now. Otherwise, I can move to the solution, which will, of course, clarify further. Okay, so let us start with question 1. Question 1 is determine the parameters to be fitted for our curve. Of course, determine the minimal set, then define the minimal solver. So, in this case, we want to fit a circle in R2, so that a minimal representation of a circle in R2 is given by its center and its radius. Its center is a 2D point, so belongs to R2, while its radius is a scalar belonging to the set of real numbers. So a minimal representation of a circle belongs to R3, and it's composed by the center and the radius of the robot. Now, we are able to estimate these parameters once we are given at least 3 points. As you remember from basic geometry, with 2 points is enough to fit a line, but not enough to fit a circle. There are 2 of them. But with 3 points, you can fit a circle. So, what you will be doing at each round of Runsack is you randomly set 3 points, then call a minimal solver to compute the center and the radius corresponding to these 3 points, and then you count how many layers you have with this estimate of the parameters. So the minimal solver that we are asked about in our question 1 is actually a way to compute the center and the radius of the circle given 3 random points. Okay, you can imagine that this might become a class, for example, in our CPP implementation, where we give this set of 3 random points, and this class has a method which returns the value of the parameters. Yes?
I didn't understand. If we are considering 3 equations because we have 3 parameters, the one of the center, 2 of the center and 1 for the scalar radius, or because for 3 points there is a circle that was into them.
Okay, so the question is why do we have 3 equations here, although we're not still there. The answer is that we need 3 points in order to uniquely determine a circle. So we need that these 3 points, all of them belong to the same circle. So we write the equation of the circle for each of them, and then this allows us to uniquely determine this C, C, and R. Actually, the answer is that we need 3 equations, both because we have 3 parameters to estimate, x, y of the center and dimension of the radius, and because we have 3 points that uniquely determine a circle. Say it's the same in the end, because the answer was, for those that are online, do we need the 3 equations because 3 points uniquely determine a circle, or do we need the 3 equations because we have 3 parameters to estimate? Actually, the answer is that we need 3 equations because we have 3 parameters to estimate, but each point determines only one of these equations. Then the answer is also we have 3 equations because we need the 3 points. Because to each point we have a scalar condition for each of the points. Okay. Actually, the fact that the point belongs to a circle with center C and radius R is expressed through a scalar condition, which tells you that the distance between the point and the center of the circle is equal to the radius. This is the condition which tells us that the point Pi belongs to the circle of center C and radius R. So this means that for each point we only have 1 scalar equation, and in order to uniquely determine 3 parameters, we need 3 of such equations, so we need 3 points. of course, the rule that you know from linear algebra that 3 parameters corresponds to 3 equations is still valid. Okay, so indeed what you do is you write down the condition imposing that the points belongs to the circle. Then it turns out that this is a scalar equation and we need 3 of them in order to uniquely determine the value of the 3 parameters. Okay, is that clear for those that are in class? Okay. So, in general, what you will have to do is you say, okay, which is the equation expressing the fact that point pi belongs to the curve. In this case, the curve is a circle, so you have this particular condition. In general, you might have the equation of a line, the equation of a parabola, whatever. The important thing when we ask you a minimal solver and when in a real application you need to write down a minimal solver in order to compute the parameters of your curve, is that you're able to write down the equation which expresses that your point belongs to the curve. Then you build the system by stacking as many equations as you need in order to determine the parameters of your curve. And then you go and solve this system by using the methods that you know from linear algebra, which might be subtracting the first from the other two and create 2 linear equations, or doing the Gauss elimination algorithm, or whatever. From equation 10, it's just a linear system that you need to solve somehow in order to get the parameters, which in this case are the x and y coordinates of the center and the radius. Okay, so again, going back to our circle, what you do is you write down the condition expressing that point pi belongs to the circle, which is an equation involving the center of the circle and its radius. Then you build a system by stacking this condition for all the points belonging to the minimal set. And then finally you use some way of solving this. In the case of the circle, the most convenient way to solve this linear system is that you go, actually it's not linear because you have r to the square, but anyway, a way to solve this is that you subtract the first from the other two, then you have 2 equations. 2 equations can be solved to find 2 parameters, which in this case are the x and y coordinates of the center of the circle. Once you have solved these 2 equations for the center of the circle, then you can plug this into one of the equations in 10 and get the radius. In particular into the first one, which is the one that you used before. And anyway. Okay, so are there any questions so far? Are you convinced that this might work to find the center and the radius? Yes, okay. So, once you have this, in the end, what you have is a minimal solver, so that given a set of points, you're able to compute the center and the radius. If you can remember, what you do in Runsack is you take a set of random points, compute the parameters, then take these parameters and count how many inliers you have with that value of the parameters. This is why in the exercise you are asked to define an error function that allows you to determine whether a point is an inlier or an outlier. Of course, in this case, a possible way to determine whether a query point is an inlier for the current value of the center of the robot and of the center of the circle and of the radius of the circle is to compute the difference between the distance between the point and the center of the circle and the radius of the circle. If the radius is sufficiently, the value of the radius is sufficiently close to the value of the distance between the query point and the center of the circle, then the point is an inlier, of course. So the idea is that as an answer to the first question, you can say that a point can be considered as an inlier if the difference between the radius and the distance between the point and the center of the circle is smaller than a given threshold. Of course, this works for a circle. For a different kind of curve, you will need to shape your error in a different way. But the important thing is that you have this concept that a point can be considered an inlier of your algorithm as long as it lies close to the curve given by the parameters that you found through the minimal solver. Are there any questions so far? No? Okay, so I can move on with the second question, that is, given a set of inliers and an initial estimate, formulate the least squares problem to optimally refine the parameters by considering only the inliers. As I was mentioning, when you have only inliers, then using least squares is a very convenient way to refine your estimate. The problem with using least squares for estimating the parameters of your curve is that least squares do not work well with outliers. But once you have determined your model and you can consider the inliers only, then least squares turns out to be very efficient to refine the parameters. So, in this case, yes?
In the error function, we are considering an inlier point that is near the circumference of the circle, not so we are taking the circumference and not the circle.
Ah, yes, thank you. So a student in the class was asking, equation 12 says that the point should lie close to the circumference, not to the circle. Okay, actually, you use Runsack to fit curves, not surfaces, say. So in this case, we are not estimating the circle, we are estimating the circumference to be more precise. Okay, so the answer, the question was, we are talking about circle, circle, and circle, but actually we should say circumference. And the answer is yes. Actually, it's the circumference that we are talking about. So this fit the circle should be fit the circumference, or at least we can live with this fit the circle, but keep in mind that you use Runsack to fit curves, a line, a circumference, parabola, and so on. Okay, so once we have clarified this, thank you for the clarification, we can go back to least squares. And as an answer to this question, you could say that as an error function for your least squares problem, the one that we introduced in order to determine whether a point is an inlier or not is actually suitable for our purpose, because in least squares we want to find the value of the state, that is the value of the center of the circle and of its radius, that minimize the sum of the error function for all the query points, which in this case are only the inliers. So if you were to solve this problem during the exam, we would expect you to write down for the least squares part, which is the state, that in this case it's an element of R3, because it's composed by the center and the radius of the circle. The error function, which you have already written for answering the previous question, and the Jacobian, which of course is, as usual, as high as the error and as large as the number of variables in the state, which is 3. So the Jacobian would be R1 times 3. Okay, once you did this, we won't ask you to write down all the theory concerning least squares. In an exercise of this kind, it is sufficient that you write down this information. Okay, so with the explanation that I tried to give. Okay, are there any other questions so far? Seems not. Okay, so at this point we are implementing, as a very brief recap of what we have done so far, we are trying to sketch an implementation in the end of a Runsack algorithm for fitting circumferences. We have said that we take sets of minimal number of samples, we get the value of the parameters for this minimal number of samples using a minimal solver, and then we go and determine how many layers do we have for these values of the parameters. And then once we have determined the model that has the higher number of inliers, then we can use least squares to refine the parameters. So, if everything is clear so far, I can move to the solution of the third question, which is very simple. Okay, seems so. So, third question. Let us take the slides for this, because probably you do not remember the formula. So I have it here. So the third question was, assuming that you have 10% in layers, 10% of points belonging to the circle, how many rounds of Runsack are needed to compute a solution? Now, as I was saying, a solution means getting a set of a minimal number of samples which is only composed of inliers. But now, given W as an inlier ratio and N as a minimal number of points, then you have that the probability of getting in K rounds all samples where we have at least one outlier is 1 minus W to the N to the K. So that the probability of failure, which means probability of having at least one outlier in all rounds up to the kth one, is 1 minus W to the N to the K. So by inverting this formula, you get the number of trials that you need in order to be sure that you have a sample, a set of samples, which are all inliers. Which means the probability of getting the solution. Once this formula is clear, then the answer to the third question is straightforward, because you only need to substitute the values of the probability of success, of the inlier ratio, and of the number of samples, of the minimal number of samples, in order to get the number of trials. I would suggest that you try to revise this formula here. Once this formula is clear, then applying it is straightforward. During the exercise part, you will have the possibility to look at the slides. Everything that is on paper. The rule is everything that is on paper. So this, you do not need to know this formula by heart, you just need to be able to apply it. It would be better if you knew it by heart, also because it's not so difficult if, again, you think of the meaning of each of the terms. Now, do you want me to comment on this? No. To comment further on this? No. Okay. Seems that we are okay here in the class. I think I can close this. And last call for questions on this sample A. Otherwise, I will move to the probability exam sample B. Okay. So here in the class, everything seems.
Second question. So we only need to define state error and the Jacobian dimension.
State error and Jacobian, and then if you have time, you can sketch the algorithm of least squares and explain where the Jacobian appears, where the covariance matrix appears, but this is the most important part. Once you have done this and commented a little bit on this, then you can move to the other exercises. I repeat the question. Sorry, I didn't repeat it from the beginning. The question was, for question 2, is it enough to write down this things here, the state, the error function, and the Jacobian. The answer is, once you have done this, if you do not have time, you can move to the next exercise. Otherwise, you could sketch the algorithm of least squares and comment further on this. But in principle, once you have done this, you can move to the rest of your work and then eventually go back to sketch the algorithm and some more details. Of course, in this case, the least squares problem is simplified also because you do not have to define the box plus and the box minus operator. Now in the next exercise we will see again a least squares problem which will need a little bit more of explanation. And also a little bit more work when you are doing that on your exam. Okay, the important thing is that you define the methodology and eventually sketch the algorithm. So, let us move to the next exercise. So, the next exercise is the following. It's called Map the Stars, and it's a least squares problem to estimate the pose of the robot in 3D and the direction of the star. So we will see why. So a robot moves on the surface of a planet that can be approximated by a sphere. The robot is equipped with a 3D odometer. When you see on your text 3D odometer, it means that we assume that we have the relative motion between subsequent poses of the robot. So we assume to have as a measurement directly the relative transformation between subsequent poses. The robot has a spherical camera that observes the sky and sees the stars. The camera can identify the stars, meaning that the stars are identifiable, so we do not need to perform data association. Data association is given. Stars can be seen as infinitely far from the robot, and so we are only able to see a direction for each star, which is identified by azimuth and elevation. Or, as you might remember from an exercise on registration, elements of the sphere can be represented as unit vectors in 3D. But we are going into this in more detail further. So, the first question, as in any least squares problem that you will see, is to follow the usual methodology, which means define the state, the domain, an Euclidean parametrization if needed, and the box plus operator. The measurements, which again means the domains, a Euclidean parametrization if needed, and the box minus. And then you're asked to write down the prediction function, the error function, and the size of the Jacobians. We do not ask you, because you do not have much time, to write the Jacobians explicitly, we only ask you to be very precise in defining the size of the Jacobians and their structure. And you can imagine that you have to be very precise in defining the structure of the Jacobian if you think that we might ask you, given the factor graph, to show the block structure of the H matrix by filling a grid. And of course, this assumes that you are very precise in determining the structure of the H matrix of the Jacobian and hence of the H matrix. Okay, but we will go into the solution afterwards. It was just to give you an overview of the problem. Now, if the problem is clear, then we can move to the solution of the first question and then examine all the exam. Okay, so I'm starting with question 1. In question 1, first of all, we need to take care of the representation of the stars, because while the robot pose is a usual element of the special Euclidean group of dimension 3, stars are identified by direction vectors, by directions on a sphere. Stars, we do not care of the distance of the stars, so we only identify them by a direction vector. Meaning that stars are elements of SC2, which is the unit sphere manifold. As I was mentioning, we have already seen this in an exercise on registration. So you should be familiar with this. Now, in this particular solution of the problem, what we do is we propose a way to represent azimuth and elevation as a rotation matrix by multiplying a rotation matrix along the z-axis and the rotation matrix along the y-axis. And we also propose a way to go from a unit vector to the corresponding azimuth and elevation. These two are just udils. I will go through them in the rest of the solution. In particular, as far as the function which computes the azimuth and the elevation given the unit vector is concerned, you can just take a plot of a sphere and then show on this plot the azimuth and the elevation, and you will very easily see that given a unit vector which points to a point on the sphere, then you can obtain its azimuth and elevation by applying the 8 and 2 operator. I propose that if you have any doubts, I take a picture of a sphere of an azimuth and elevation and show you this in more detail at the end, after we have finished to see the methodology. Okay, so again, let us talk about domains. And as I was mentioning, we have that the robot, the pose of the robot is identified as an element of the special Euclidean group, while stars are element of the unit sphere manifold. In the text, you have seen that we have n poses and m stars, So the dimension of the state as a whole will be the Cartesian product of n poses, which are elements of SC3, and m stars, which are elements of S2. Now, as usual, once you define the manifold, you also need to define a Euclidean parametrization for it. The Euclidean parametrization for ST3 is the usual one, is R6. While a possible Euclidean parametrization for the unit sphere manifold is R2, because we have an azimuth and an elevation angle. So the perturbation as a whole will be as large as 6n, because n is the number of poses, plus 2m, because m is the number of stars. Now, once we have defined the Euclidean parametrization, we need to talk about the box plus operator. Of course, the box plus operator for the SG3 manifold is the one that you know very well. It's V2T. But as far as the star is concerned, we can imagine as a possible box plus operator to build a rotation matrix out of the azimuth and elevation angles of the Euclidean perturbation. Why? Because, of course, when you compute the rotation matrix, which is the composition of a rotation along the z-axis and the rotation along the y-axis, when you compute the rotation matrix associated to a Euclidean perturbation, which is an azimuth and an elevation angle, and apply this to an element, to a unit vector pointing to an element of the sphere, then you obtain another element still belonging to the sphere. As usual, what you need to check to know whether your box plus is a suitable operator for your problem is you need to check that when the perturbation is 0, then you stay on the same point on the manifold, and that whatever perturbation you have in terms of azimuth and elevation, you will still get an element of that manifold, which in this case is the unit sphere. Okay, this is from a theoretical point of view. You should think of these two guidelines when choosing a box plus. So the box plus with a 0 perturbation should provide the same element of the manifold, while the box plus should always give again an element of the same manifold. But in the end, when doing the exercises, if you think about it, you always tend to use rotation matrices to reconstruct an element of a manifold in order to apply a perturbation to an element of the manifold. So probably while doing this exercise at the exam, it would be very natural for you to write down the vector 2 transform as a box plus operator for SC3. Probably you would have some problems in imagining the box plus operator for the element of S2, but in the end you could get to the correct solution if you think how you should apply a perturbation in terms of azimuth and elevation to a point on the sphere to obtain another point on the sphere. And rotation matrices are a good solution. Of course, you need a little bit of experience, but also just to think about it in order to have the right ideas for box pluses. But so far it is, sufficient that you understand that the vector 2 transform is a suitable operator for the SU3 element, just as a rotation matrix from an azimuth and elevation angle is the right solution, is a suitable solution for elements of the unit sphere manifold. Okay. Do you have any questions so far? No. Okay. As usual, once you understood how to deal with the state, then you should move to the measurements. And measurements are represented by, again, angles, because measurements are azimuth and elevation of stars. I will correct this because measurements are represented by angles. Measurements are again elements of S2, of the unit sphere manifold. And indeed, we have the necessity to define a box minus operator because the measurements are angles and are non-Euclidean. So, before getting to the box minus operator, let us briefly discuss how you can formulate the prediction function. Now, as usual, the prediction in least squares is that function which returns you the measurement given the current estimate of the state. So in this case, the prediction should give you the azimuth and elevation of a given star, which in this case is XSI, it's the ith star, given the current estimate of the star and the current estimate of the robot pose. As stars are very far from us, then we can neglect the translation and only rotate the unit vector, which gives you the star on the unit sphere, to obtain the star in the robot frame. And then once you have the direction of the star in the robot frame, then you can use an operator in order to get the azimuth and elevation angles. As you might remember, gamma is the operator that we use to identify the function which returns you azimuth and elevation from a unit vector. There are many things that you can do. You can decide that you leave Z, that you leave your measurement as a unit vector, then you do not need the gamma operator. Or you can decide that you want to turn your unit vector into a set of angles, azimuth and elevation. Then you need the gamma. But the important thing is that whatever choice you make, then you stay consistent. So if you decide that your measurements are unit vectors and you represent them as elements of R3, then it's okay, but be consistent with this. when you compute the Jacobians, when you tell the dimension of the Jacobians. Otherwise, you say, no, I have an operator which gives me the azimuth and the elevation out of a unit vector, then it's okay. Then your measurement will be an element of R2. Then in your Jacobian, you will have blocks that are as high as 2. After you have defined the prediction function, then you can move to the box minus operator in case you need it. Because as I was mentioning, it might be that you decide to keep your measurement as a unit vector, then you will have the chordal distance as a box minus. Otherwise, you can decide that you turn the measurement into a rotation matrix, and then, as an example, you can use equation 19, where you're saying that your prediction should be as close as much to your measurement, and this can be expressed by the fact that the product of the rotation matrix obtained out of the measurement transpose times the rotation matrix obtained out of the prediction should be as close as possible to the identity. There are many things that you can do. As far as the exam is concerned, I would suggest that you keep in mind 2 or 3 possible solutions, such as the one that you find here, and then use one of these. The chordal distance, chordal distance, is of course you can use that in many different settings, in many different problems. So keep it in mind because it might be very useful when you are to solve your exam exercise. As you might, I know it's the first sample, it's the first sample of exam that you see, so probably it seems very complicated now, but when you go through this at home, please focus, please notice that you have different levels of understanding of the problems, and that when you are in front of a new problem, then you might be able to give a description, a general description of the problem, but not go through all the details, but this is okay for the exam. So keep in mind that here you have, as I was saying, different levels of understanding. One level of understanding is that you say, okay, the robot belongs to S3, the star belongs to S2, the Euclidean parameterization is this, the box plus for the pose is this one, but I don't know what box plus I can use for the star. And this would be already something to write down in your exam. So my suggestion is when you go to solve the exam, write down step by step everything that you understand, and then the solution will come very naturally if you start writing down the things that you already know and things that you understand well. In order to complete your exercise when you are at the exam again, it is not a problem if you do not detail, for example, the prediction function, but at least give the idea that you need a box minus, write down the dimension of the measurement, so that you can solve the last part of the exercise, that is so that you can write down the dimension of the error and of the Jacobian. At that point, once you have defined the methodology, once you have defined the domain of the state, the domain of the measurement, once you have said that you need the box plus and the box minus, and once you have defined the dimension of the Jacobian, then the problem is almost solved as far as the exam is concerned. Then, of course, the ideal solution is that you are also able to write down the prediction function and the proper box minus. So, as far as the Jacobian is concerned, again, we have that in our particular choice of the box minus, the error has dimension 3, so the Jacobian is as high as 3 and as large as 6n plus 2m, because of course it is as large as the perturbation, which we have seen, that is 6n plus 2m. And then what you can do is to write down the structure of the Jacobian for the two kinds of error function that we have. So we have a post-pose error function, but we also have a post-star error function, and you are supposed to write down an example of a block for each of them. So, for example, the post-pose error function will have a Jacobian that is as high as 6, because in the post-pose error function we have a relative transformation between poses, and as large as, again, the dimension of the variable of the perturbation, which is 6n plus 2m. In this case, you will highlight that for each post-pose error function you have a non-negative block for each of the two poses that are involved in that specific post-pose measurement. Assuming that we have pose I and pose j related by a measurement, then we will have the ith and the jth block, which are non-zero. As far as the pose-star error function is concerned, as I was mentioning above, we have a 3 times 6n plus 2m block. And in this case, you will have to highlight that you have a non-zero block for the pose, and a non-zero block for the landmark. Of course, the dimension of the non-zero block for the pose is 3 times 6, while the dimension of the non-zero block for the measurement is 3 times 2. Again, when we talk about the structure of the Jacobians, we mean this. We mean that you understand that we have, in this case, two kinds of error function, and that for each of them you specify the dimensions. And eventually write down the non-zero blocks and what are their dimensions. Keep in mind that when you're doing your project, you will have to think about this a lot. Because in your project, you will have presumably at least two kinds of error functions, at least two different kinds of measurements. So you will have correspondingly blocks of different dimensions. Okay, so if you have questions on this, then I will take it and then move to the grid, which is the last part of the exercise. Okay. Okay. So now I will show you the last part, and the time is already almost gone. So I want to take here this. Okay, so given this factor graph, when you are to fill the blocks of the H matrix, what you do is that you have a non-zero block in the H matrix whenever two variables are related by a measurement, which in the factor graph is represented by a factor node. So this part of the exercise is very simple, because what you do here is you have that x2 is related to x1 through an odometry measurement, so you have this non-zero block here. Correspondingly, you have a non-zero block also here, because as you might remember, the H matrix is always symmetric. Then, so the part related, the part of the H matrix related to the trajectory is very simple, because you have that odometry measurements relate subsequent poses, so that you have a non-zero block for x1, x2, a non-zero block for x2, x3, and a non-zero block for x3, x4, and then you're done. So this diagonal block here corresponds to the trajectory part of the factor graph. It is more interesting to fill in the part of the H matrix related to the landmark, because in this case you have to be very careful. And indeed, to make an example, the fourth pose of the trajectory is related through a measurement, which is represented by a factor node, to the first, the fourth, and the sixth, the fifth, and the sixth landmark, so that if you take the fourth row here, you see that it is related to the first, the fourth, the fifth, and the sixth landmark. So you have a non-zero block in the H matrix in correspondence of the first, fourth, fifth, and sixth variable of the landmarks. As a final check, when you're doing this kind of exercise, always check that the matrix is symmetric. If it's not symmetric, then you missed some factor node between a pose and a landmark. And this won't be a big problem unless you let an H matrix non-symmetric, which means that you didn't understand the theory. Okay, so this is the typical error that we know that probably it's just that you didn't see a link, but having a non-symmetric H matrix is a conceptual error, so this would penalize you. Okay. So, if you have any questions on this, then again I will take them. Of course, you remember that H is equal to J transpose omega J, so that you are able to tell the dimensions of each of these blocks and do that at home for your exercise. In order to have a further grasp on the dimensions, so that when going to the exam, you won't find many difficulties in telling the dimensions of the blocks of the Jacobians. Okay. For this last part, my suggestion is write down the dimension of each of these blocks, check that this is consistent with J transpose omega J, and again check all the dimensions and be sure that when you go to the exam, although you don't write all formulas in detail, but at least you make us understand that you know the manifold theory, that you know the methodology, that you know how to define a box plus and a box minus, and that you write the correct dimensions. As a box minus, which is always good to keep in mind the chordal distance. Okay. Again, also in this exam sample, please have a look at home, because we do not have time, to the filtering exercise, which is indoor localization. And in this exercise, you will have a specific case of a measurement function, which is given by the time needed to travel the distance between the beacon and the robot. So it has an interesting measurement function that you should see in preparation of the exam. And another characteristic is the time delay between the receiver and the transmitter, which again is an interesting exercise for you. Then this is an example of a theoretical question, and it's data association. Try to answer also this question and to imagine other questions that we might ask from the theory. Okay, so I would say that we can close here, because it's already 1 past. Let me check if the streaming is okay, if the professor is watching us, and then I will close the streaming and wish you a Merry Christmas. As we are done. So, okay, let me just have a look at the. Okay. So I am closing the streaming actually, and if you have any questions, have a look at the filtering exercise. I have already pushed everything. Have a look at then again at these exercises, and if you have any doubts, please just write an email. So wish you a Merry Christmas, and